and thank you for taking the time to be here. We are from Thorogood, an independent consultancy firm with wide machine learning experience in projects for a wide variety of clients. Today, we'll be discussing a use case combining the aviation industry and machine learning, revolving around the prediction of flight overbookings. For this particular use case, we are using example data to showcase one of many possibilities to use big data in combination with aviation businesses to generate insights and efficiency. I'm Fernando, and I'm joined today by my colleague Michele, who will tell you some more about this interesting use case.
So today we're going to present a use case, a machine learning overview, and a tech demo. In order to reduce loss caused by traveling with empty seats when passengers don't show up, airlines commonly overbook their flights to make sure every seat will be occupied. And because of that, airlines even pay passengers to take an earlier flight than what was previously booked to fill up seats or overbook flights to guarantee all will be filled. So when you have an accurate forecast of the expected number of people to actually show up based on a set of passenger types and characteristics, you're most likely to increase your revenue. But how can you have a more accurate forecast? Today, we're going to show you how you can leverage your data to do so. So first step is to collect data from airlines' previous flights. Next step is to use machine learning to train a model to predict no-show rates based on historical data. And then finally, we can apply this model to future flights to determine how many seats should be overbooked. Now, a machine learning overview. Why do we use machine learning instead of just using if-else conditions? That's because machine learning can build much more complex models than creating if-else rules. With if-else, if we don't have data about a specific point we want to predict, we're going to have to guess the forecast result based on the closest data we have collected. And besides that, if we have a big data set, the if-else rules will be manually written, and whenever new data comes in, the rules would again be manually reviewed. And because we're creating the rules by ourselves, it's likely that we will have biased results, while with machine learning, we can get insights that we wouldn't imagine if the rules were created by us. Also, with if-else, probably a lot of rules will be created, and for each prediction, the algorithm would have to check if by if to see where the prediction fits. And in the opposite side, machine learning builds systems that learn or improve performance based on the data they consume, minimizing human intervention. And to do so, the process is usually like this. It's necessary to process your data, to build your machine learning model, use your process data to train the model, use a portion of your data set to validate the model you built, you deploy your model, and you keep monitoring it to make improvements if necessary. Now we'll go back to Fernando for our tech demo.
Thank you, Michele. Let's now dive into the practical part, where we'll go through a simplified machine learning pipeline, following the steps Michele just discussed. But before, let's discuss a couple of important concepts. As you know, we are trying to predict if passengers will actually show up to flights. Therefore, we have two possible outcomes: people who likely show up and people who likely won't show up. For ease, we'll call each of these classes as show and no show. Therefore, we have a classification problem. And in this type of problem, we are trying to attribute every passenger one of two outcomes, a binary outcome then, as opposed to a regression problem where we would try to attribute a continuous numerical value to a prediction. The second kind of problem could be, for example, in a use case where we try to predict ticket prices for flights. To solve this classification problem then, we need a classifier method. And for this, we use the logistic regression method, which is a statistical analysis method to predict a binary outcome, such as show or no show, based on prior observations of the dataset or historical data. In order to evaluate the success of this method in classifying a test dataset, we use the test area under the receiver operating characteristic curve, or the ROC curve, a commonly used parameter to evaluate a binary classifier system as its discrimination threshold is varied. In an overview of the process we will be following, all the way from the raw flight data to data treatment and filtering, processing the data, one hot encoding the categorical columns, training the model using the logistical regression method, and finally, the evaluation process I have just mentioned. I'll keep this graph in the underside of my screen so you can keep track of what we're talking about. Now that I have Databricks opened, let's start by viewing our raw data set. First, I have imported some libraries here. We can finally see our data set being imported. We are working with a passenger names record file, or PNR for short, with some of the features we need in order to build up our model. This raw data includes a couple of some columns which will be used as features, but first we need to filter the data. We are filtering it to not have any nulls in the data. This is needed because of the method we're using, the logistical regression. It does not accept any nulls in the data. Next, we can process the data. This data set we have is a very wide data set, including flights with destinations and origins from all over the world. It would be good and less biased for us in a simplified model to make all the flights have its origin and destination in the US, and that's what we're doing. To do so, we are first getting a list of all the airports in the US and joining to only these airports which have its origin and destination within the country, and also convert all of the currencies that the tickets have been bought on to US dollars. After that, we can have a little look at the data and how it looks like now. As you can see, we can see the counts of how many records we have, the means of the records, standard deviations, maximums, and mins. We can also see that all the currencies are now converted to US dollars, and we have both destination and origin to airports in the US. Next, we can follow up to the one-hot encoding. As you see, we have some categorical columns, such as destination, origin, business leisure, or cabin category. Since the logistic regression is a numerical method, we cannot input categorical columns in it. So we need to identify or convert these columns to numbers, to numeric columns, and therefore we one-hot encode. This way, with this method, we can also attribute numeric values without giving any extra weight to any of the features, making the models too balanced. Next up, we can start with the training. We have a training and a test data set first, divided in a random split of 80% for training and 20% for testing. The training data set is not balanced. It is composed of 86% who people will actually show up to the flight and 40% of people who will not show to the flight. If we train with this data the way it is, it can cause a bit of bias in the model, meaning that the model will think that most people will always show and less people won't show. And we don't want to bias the model. For this, I'm balancing out the model, getting only 14% of people who will actually show and all of the people who won't show, making the model roughly balanced in both classes. After training, we can plot our first curve, our RSE curve. It shows in the graph our false positive rate versus our true positive rate, generating our RSE curve. From this, we can calculate the area under this curve, which is for the training set, again, 0.97. This is very close to 1, and it means that we are reaching a very high false positive rate at any of the true positive rates classes we have. Again, this is only for the training set, but what really matters is testing the model in a real-world data set. And this, of course, is our test set. The test area under the ROC is also very close to 1. It's 0.96, meaning that we have a very good model with relatively good recall and precision. We can see our model performs well, but now let's check some of the predictions. After disassembling our vector, we can check our precisions considering some of the features. Here, we can see total amount, number of passengers, business or leisure flights, and the actual show or no-show class. And here, our prediction. As you can see, if I quickly scroll down here, we have correctly predicted most of the cases, except for this one in this example. And this is likely because this value of total amount of US dollars paid might be an outlier, too high regarding the mean values, and it may have influenced in the final outcome. Okay, let's go back to the slides and I'll finish up. So again, thank you for your time here. And if you have any questions, please feel free to reach us out via LinkedIn or via email. If you have any questions about a specific data set, any application or use case you might think you can use big data to generate insights and improve your aviation business, please let us know. You can also reach us through our website. Thank you so much for your time and see you next time.